go. So anyway, it says we're going live, so I believe we are live, ladies and gentlemen, just like every smooth start we do for every one of these shows. Thank you for being patient with us. Instead of preparing for this, I decided I'd build my new computer, which let me give a little brief, little view in this mess over here. I don't know if you can see that, but that's going to be our new streaming machine in that wooden box. And we'll see if it catches itself on fire. It might. Oh, and I did the whole thing where I have our own audio going. So everybody mute the YouTube streams you got going. We're professionals at Space Force Theater. And, you know, tonight I want to point out something. I'm sure you've already noticed it. But tonight we decided it was time for the white man show. That white men don't get enough. Exactly my point, Jared. Sarah bailed on us. I actually had some planned guests, and as you know, I like to. Anyway, I had some guests planned, but it turns out that she needs to get some permissions. We can't even say her name, can't talk about her. But we had big plans, and I have other plans lined up, and I realized that right now this looks pretty bad. So we're going to stay away from any topic that, frankly, white men should not be proclaiming we know anything about. And we're going to stick to science tonight. We're going to stick to astronomy. We're going to stick to science. We can speak from our hearts on things that are affect us, but otherwise, I'm not going to pretend that I'm a leader on any of these other topics that I'm actually finding very interesting and I wholeheartedly support right now. I just think it's too many people think they're speaking from authority and they're not. And I want to make that very clear. I don't think we have any authority based on who's on our show tonight, but we do know science and we know other things. And anyway, if we get on those topics, that'll be great. So anyway, I want to welcome from my left to my bottom. I know on everybody's Zoom it's all different, but Bill Grunenberg, hello. Say hello to everybody out there.
Hello to everybody out there.
Oh, perfect. Thank you. And also with us tonight is Jared Head. Jared?
How's it going, everyone?
I hope we're doing well. Like I said, tonight we're doing a free flow of show. Since my guests didn't fall through, but wisely decided, maybe I should make sure I have approval to go on this sort of a crazy show where they drink whiskey and have laughs. No, actually, the person's very excited to be on it, but it doesn't have approval. So
I just realized I don't have a drink. Oh my gosh.
You can grab one. I'm
going to go grab one right now.
I'll keep the troops entertained. So anyway, I decided, well, let's do a show anyway. I've got things to talk about. There's news, there's space news. And then we thought, well, why don't we do the Catherine Wheel of Doom, or the Cosmic Catherine Wheel of Doom, as I was calling it. And that really is just us going to the YouTube stream and finding out what you guys have to say. I'm going to go to live chat now, although, is there a chat? Welcome to chat. It pretends I've never been to chat before. Stop that, you terrible thing. Pop out the chat. There we go. So anybody that's in the chat right now, logged in watching us, if you want to let us know what you want to hear about tonight, we'll jump on those topics. They're going to type in the chat. Anyone out there?
All five of you.
All five of you have logged in? Well, we're getting there. Oh, it's early, though, with these summertime. Well, we're not quite summer yet. Summer started on June 20th, so we're still a couple of days away, but nearly summer. It's light out. People are eating. 8 o'clock seems too early for a show like this. So we'll let people get here, and as they log in, we'll get there, and we'll take questions. But I had a question. I saw a result about, my dad brought it up. Hi, Dad, if you're out there. Billions of Earth-like planets. And evidently that something was going on with it. So I'm going to Google that. Billion Earth.
Billions and billions and billions.
Billions.
Earth-like planets, as many as. And the study says, oh no, that's a really old one. I don't trust that one. Billion Earth-like planets. And by Earth-like, what do we mean? We mean that the planet is roughly the size of Earth, rocky, small, not a gas giant, not a mini Neptune. And by Earth-like, it also needs to be in that habitable zone where you're at the magic distance. Well, it's not magic. You're just far enough away that it melts the ice. Close enough to the sun that it melts the ice, far enough away that it doesn't vaporize at all. So you have liquid water on your planet. And I did bring up the story. So turns out that it looks like it's a study based on the Kepler telescope, which found thousands and thousands of planets out there. And they did a new calculation. They looked at all the stars out there and estimated that the sun-like or G-type stars should have about 18% of them should have an Earth-like planet, which is almost 20% of them. And our galaxy has 400 billion stars, and 7% of those stars are G-type, so it's a little less than 10% of the total. So you multiply that out, and then you multiply it by 0.18, a little less than 20% of them, and you end up getting that there are roughly 6 billion Earth-like planets. So that's a lot of them. I don't know if that affects our number we did last month when we did the Drake equation. I wonder if it affects the number of piano tuners in Santa Barbara.
It could.
It might. It could. But no, but we did the Drake equation. And of course, you multiply all that out and you get a number of aliens. And
I think that's actually close to the number in my personal one.
Is it?
I think I think mine was somewhere like 7 billion, somewhere in there.
For Earth-like planets. Now, how many of those develop life in your?
Well, mine were for habitable planets, just in general. So.
Oh, well.
So, Earth-like, that's an extra stipulation.
What does habitable include for you besides liquid water temperatures and pressures and all of that? I mean, is it rocky and is it Earth-sized roughly, or no, or just?
Well, mine was just sort of like a general assumption for public consumption. So. So it's mine was not made with the microscope that all three of us would put it under if we were doing it amongst our peers.
Right. Well, and by the way, I just noticed that Sarah is on our YouTube chat. She's spying on us all, so she's here to mock, but she's not here to participate. So anyway, on the chat, you're only allowed to correct us 9 times per minute, I think. So that'll keep us online. No, we're going to greatly. I do want to point out that Sarah's not here tonight. We're going to greatly miss her. She had some things she needed to take care of. But yeah, I don't know what we're going to do without her tonight. We'll make do. We'll make it all happen.
Mm-hmm.
So anyway, that is very interesting. The number you're going to hear the number of Earth-like planets change. It'll go up. It'll go down. Different people will analyze things differently. They may say, well, for it to really be Earth-like, it needs to be in maybe a more narrow range. Eventually, folks are going to start to get spectra of these, which means you take the light, break it into its components, and you'll see the components of the atmosphere of these planets. Now, it's going to take a lot of work to do it for ones as small as Earth, but maybe with future giant telescopes that we want to build, we might be able to do these sorts of things, and it could be kind of cool. Anyway, let's see here if we have anything from our audience out there. I see that Fangirl Academy's out there. Nobody's asking any questions. We still have 6 watching, which is pretty great. So we're on a roll tonight, everybody. I'm going to bring up over here, I'm going to jump to some PowerPoints because I wanted to go into installer. Well, let's see here. I may have to dig around a little bit to find it. Anyway, maybe I can just talk people through it a little bit. Last month's, or the last All Space Considered that I did, a friend of mine was at it, Dan Kelson. I was attempted to bring him on the show at some point, but it was a very interesting result with talking about the growth of structure in the universe. And he got down into the nitty gritty of the equations and everything. But what I thought was particularly interesting about Dan and what he was showing us all is that, first of all, they made a prediction. They did the theoretical work, him and his colleagues. So they took the physics that governs the universe. And we think you start out with a hot, glowing universe. It has some regions that are a little hotter than others, a little denser, and that slight density changes, the slight temperature changes that go along with it, that means gravity is a little bit stronger there, and it can start to pull things together. But nobody really knew how quickly those densities should grow, because to go in and calculate, how do you pull on this bit of the universe? How do you pull on this bit of the universe? How do you bring it all together? To take that and compute it, it's impossible. We don't have that CPU power. Even to do from one galaxy to another in a large array, we have to make estimations to make this happen. It's a whole field of study that people do to run these simulations. Well, Dan and his colleagues thought it through and said, instead of trying to learn about what one little area does and how that one area would grow by looking at everything around it, let's just look at averages. Let's take, on average, things that are as dense as the region around the Milky Way and our galaxy, as Andromeda, another big spiral there. How big should that grow? How quickly should we draw more material into it? How quickly should the area transform in its density, and how quickly should it go up? Well, they thought, well, let's just average across all the equations. So you do averages, and when you work through all the math, and it's, Dan was being very nice by saying he wasn't good at math and, you know, whatever. He's darn good at it. That was not necessarily the easiest stuff. Goes in, you average it, turns out that the prediction is density should grow, first of all, with the square of how dense you are to begin with. So that's something like, oh, I'm feeling pretty dense tonight. So no, that isn't, you know, that density isn't going to grow. But in terms of density, we mean how much mass is there per volume. So how much did you start with? How many stars were there per volume? How many galaxies per volume? How much gas? How much dust? How much all that stuff? So if you know how much you started with, they predict, well, you should start growing faster if you have more. Areas that started with less should grow less. In fact, if you have twice as much stuff, you're going to grow 4 times faster than an area that only has 1 times the stuff. Then they went in. Yeah, Bill.
So it's exponential growth is basically what you're saying, right?
Kinda. It's squared. So it's exponential in you're squaring with the square of the density. It also goes with the square of the time. So as if you wait, you know, 1 billion years, things will grow so fast. If you wait 2 billion years, at 2 billion years, you'll see all the densities 4 times denser.
Mm-hmm. Mm-hmm.
And everything scales. So you see this sort of collapsing of densities into much denser environments rather quickly. And every time you double the time, the stuff that was denser gets even faster, the density increases. So it's a rapid growth is what they would predict on that. Then, because they work at Carnegie and they're part of studies and they're very smart and have access to large amounts of data, they went and had 100,000 galaxies and they measured these galaxies of how many stars are in the galaxies. And you do that by looking at how much light is in the galaxies, and not just a single amount of light. They figured out essentially colors, and you go in and say, well, how do we make the galaxy that color? We need so many stars that are red, so many stars that are green, so many stars that are blue, and it's a little more complicated than that, but that's the basic idea. From that, you can say, well, that star or that galaxy has 400 billion stars in it, and they weigh this much because we know how much a hot young blue star will weigh, and we know how much a young little red dwarf will weigh, or an old red dwarf, for example. And when you add all that stuff up, it turned out they can track on average across their samples, across time, the growth of density, and it matched what they predicted. So now what does that mean? Yeah, go ahead.
I was just going to say, and so that's ongoing. It's not like we're at the end of that process. It's going to continue, right?
Yeah, well, the densities are still growing. It takes a very long time, of course. We're not going to watch anything over human lifetimes. Right. But in terms of predictions and seeing where it could go, that seems to be the case. Yeah, it should keep going. I don't see what would stop it. Maybe if you drop things into black holes, something might get weird. But even that, I don't know. If you continue to pull stuff along the filaments and you continue to flow in towards these denser regions, again, these are all flows. It's a way to think about it is mass is flowing in the universe downhill, sort of. Mass bends space-time, and that bend makes things, when they travel on a straight line, to head towards where the mass is. As crazy as that sounds. Because gravity doesn't really pull on you.
So it's mass all the way down.
Yeah, mass all the way down. It's not turtles. Turtles have mass, though.
Turtles are a kind of mass, really.
They are kind of mass.
But this also means that the less dense regions are getting even less rarer.
Well, yeah. You could turn this whole thing around, I believe, and have, I don't know if you could do it for an inverse gravity and think of empty space as having, find the densest region and then back off from there and pretend you're adding anti-gravity particles to each amount of space. And in the voids, where there's almost not quite nothing, but where there's very little there, very few galaxies, you'd have the least amount of matter and the most amount of this anti-gravity stuff. Yeah, you could probably redo all the equations that way. You'd get exactly the same answer. You'd have the underdense regions would grow, and they'd swell and the dense regions would collapse in on themselves. Because I think it would all work.
So my question then is, they know that they're on the right track because they look back in time with, the higher and higher redshift and see that what they described is happening over time.
Exactly. Yes.
Yeah. Cool. Very cool.
Yeah, they are able to go in and see over time that not only, well, it's on average, again, you can't go to a single galaxy, you can't go to a single cluster, but on average, in their sample size, which is hundreds of thousands of galaxies, the ones that are further away in clusters, those clusters and those galaxies had less mass. And the way they look at the nearby ones that are much older, they have grown, essentially. You can say, the things in those regions and those environments, they are now denser by a certain amount, by quite a bit. So it's kind of a neat result. It really is. I'm going to look here and see what else has happened in the universe.
I do have a question from the chat room.
Yeah, what is our chat one?
There is a question in the chat room.
Yeah, run it by me.
It's Aqua Monkey EG or Aqua Monkey Egg, whichever. I don't know which one. Aqua, let us know.
Monkey, for example.
They're asking, how long would it take to catalog all the stars in the visible universe?
Too
long.
Yeah.
Well, we'll calculate the number of stars in the visible universe. Who has a calculator out? Do I have to do this math? It might break my laptop. If it crashes, I'll come back. I promise. Well, there's roughly, let's say, 400 billion stars in the Milky Way. It's just roughly. There's somewhere on order of 500 to 800 billion galaxies in the observable universe. Now, not all of them are very big. There are some that are really, really small, especially way back at the beginning of time. The ones that are just forming, they don't have a whole lot of stars in them. But let's just assume, for the sake of ease, each galaxy has even 100 billion stars. So that's 100 times 10 to the 9. We don't need to go trillion. And then we're going to multiply that by the number of galaxies. And let's say, just for ease, there's 500 billion in the observable universe. And by observable universe, everybody out there, what we mean is, from our vantage point in the universe, as we look further and further away, we're going back in time. Just like we were saying, those galaxies my friend Dan Kelson analyzed and Louis Abramson analyzed. As we look further away, we're seeing them back in time. But if you look far enough away, you get to a point in time where galaxies didn't exist. You hadn't made stars. You hadn't done anything. So that bubble around us, we sort of consider the observable universe. Because if you go far enough away, even still, it gets dark, and then you run into the cosmic microwave background radiation, and then you actually hit the beginning of time. Well, visible light doesn't get there, but conceptually, you can see you could get there. And so you only have a bubble so big that you can see. So we're going to assume that bubble has 500 billion stars in it. And 500 exponent 9, and it's going to break my calculator. No, 5 times 10 to the 22.
Yeah.
What's times 10 to the 22? Does anybody know
There's no word.
That would be like 50 billion trillion, I think.
I don't know.
I want to say.
Yeah, it would be 50,000 billion, I think. Because 9, that's 18, and then you get 3 more. That's 1,000.
It would be
5,000 billion.
I think it's just 10 to the 22. Trillion is 10 to the 12. I don't know what's after trillion. Order of magnitudes. Here we go. Do they tell us on Wikipedia our favorite?
Well, if it's 22,
21 is sextillion, and we're 10 to 2. So this is 50 sextillion.
Wow.
Is that the right number?
It's a lot.
50 sextillion, everybody. That's how many stars are in the observable universe. So let's say it takes us even 1 second to look at each one, to analyze it, to catalog it, which is impossible. Astronomers don't work that hard. So divide that by 3,600 to get hours. And we're at 1.38 times 10 to the 19 hours. Well, let's divide by 24 to get days. This is long. And that's still 10 to the 17 days. Let's divide by 364 4.25, close enough,
5
days per year. That's still, oh gosh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's 1.5 times 10 to the 15, I think.
Yeah.
Why it's not showing it to me in
Years are
scientific notation when I'm on a scientific calculator, I don't know. But so that's quadrillion. So I think we're 1.5 quadrillion years for us to analyze every single star. So
that's
it's longer than the age of the universe.
It should be pretty easy. It should be. If you get funding for a program that long, it shouldn't be too hard.
I don't need funding for a program that long. I need whiskey. So tonight's show is brought to you by Pinhook Straight Bourbon Whiskey.
So that's what you're drinking.
This is what I'm drinking. Actually, it's a gift of my friend, birthday gift. They name the whiskeys they make after champion horses that won. So this horse was 15.3 hands tall. Anyway, yeah, it was brown. It's 47.75% alcohol. I don't know how a horse that's 47.
I don't know either.
Wins anything.
I was like, that's the hand, but I'm not a horse person. My sister's a horse person. I should ask her.
I don't know anything about horses other than that there's apparently 180 of them under the hood of my Jeep. So
nice.
I don't know how they all fit in there, but they do apparently.
Yeah.
Hey, did you know that turns out planets with oceans are common in the galaxy? In fact, not only common, it's likely.
Likely?
Yeah. This might be the same study we were just talking about, but a different write-up. So this is from NASA. No, this is through a mathematical analysis of several dozen exoplanets. So clearly this is a huge sample. Okay, to mock astronomers a little bit, I'm sorry. But included the nearby TRAPPIST-1 system, they think that by measuring heat emitted from an exoplanet or detecting volcanic or cryovolcanic activity, maybe we could see whether they actually are active. So they're thinking that some will be measurable. We'll actually be able to tell.
Yeah.
Nice.
Whether there's activity on it or not.
That would be pretty good.
Would be, but that's not the story I wanted to talk about.
I have an exoplanet-based question for you, though. That's conceptual.
Who?
You want to know, or should I wait till later?
No. What do we have? This show again is the cosmic Catherine Wheel of Doom. That the audience is supposed to stun us and stupefy us with their ideas, and if they don't, we will. And I'm doing a pretty good job of it.
I will say there are more questions in the chat room right now, but Bill, definitely take it away.
Well, keep them coming.
I've just been musing about this, and my muse has been if we lived in, I don't know, just several hundred light years away from this solar system, and we were on exactly the right plane that, Mercury's orbit compared to the ecliptic is way off. It's like 7 degrees off. So if we had a point of view where Mercury was exactly, the Kepler-like transiting planet, would we be able to detect how much of the rest of what was going around the sun is there? In other words, radial velocity or something once we found a transit. In other words, if we're looking at our solar system and the only thing we can see is Mercury transiting, how much would we know about whether there were other planets, whether they're large planets?
Right. Well, do I get to game it? Like,
yeah, of course.
If we're going to have Mercury just clipping the edge of the sun, so we're at 7 degrees off, but it's off, we might be able to get within 3 degrees of the others. And I think that might buy us Venus and Earth. My memory is that for Kepler, for the inner planets, but I don't know how inner it is, we would get roughly 5-ish%. And that was due to the tilt.
Oh, okay.
The other 95% we're going to miss because the tilt will be too much and they won't transit or cross the stellar surface. That's my memory. It's probably roughly correct. It's probably not off by more than a few percent. Can't be more than 5% too big. It feels like it's a little too big, but it does depend on one, how far out. So Earth is further than Venus. I bet it would catch Venus. Earth, maybe not.
Yeah.
Probably Mars, no. Jupiter, probably not. And that is also why, the Kepler Space Telescope saw lots and lots of planets close to their star for that very reason. You can have a pretty big tilt and you're still going to cross in front of the star. Whereas if you're far enough away, well, no. you got a big lever arm on that tilt. It moves you away. So it's a good question. Now, what's some questions from our audience here? Although we don't take any from Sarah Vincent. I'm sorry.
Okay. Well, thankfully, Sarah knows everything, so it's all right.
Well, no,
we have Fangirl
tonight because if she's asking questions, she's setting us up. She doesn't want to know anything.
Fair enough. So Fangirl Academy actually wants to know.
Oh,
see, then Jared goes away here, right? And he'll come back and be like, so can you answer that?
He wants to know.
Come on. Oh my gosh, my internet. I swear.
Right,
this internet's killing me.
You glitched out right as you said Fangirl Academy wants to know.
What are you sipping on, Bill?
What am I sipping on?
Yeah, sure. They want to. Yeah, Fangirl Academy wants to know.
Okay. I have one of my favorite drinks. My wife and I don't drink during the week. We wait till Friday, Saturday, Sunday. And so this is my gin and tonic without gin. It's my and tea, I call it. And tonic. That's it. It's tonic, lime juice, and ice. And nothing else.
Nice. Very nice.
But we keep the rule.
All right, I'm just going to show some pretty images here because I can. Well, it's a Hubble release. It's Hike 2011 photo release. And I thought this was an old Hubble image. Maybe somebody at Hubble is just, they're home, they're bored, they're in the middle of this pandemic, and they've decided, well, let's just show some pretty things. So here we go. I'm going to take over the sharing, everybody. Share screen, and here we go. So this is an image of a planetary nebula. Does everybody see that okay?
Ooh.
And I'm going to go to the full size.
Oh, 6302. That's the one that I imaged for the imaging class we just did.
This is the one you played with,
yeah,
Bill?
That's not my image, but I did. I'm going to put it back up for you.
So anyway, what we're looking at here is actually what's known as a planetary nebula. And this is the remnant of a roughly sun-like star after it dies, so to speak. So our sun it roughly is about halfway through its age. It's converting the hydrogen into helium in its core. When it runs out of that hydrogen, the helium is going to start to collapse. The outer layers will start to expand to let out the extra energy. Believe it or not, as that core collapses, it gives off more energy than it's giving off when it's doing the hydrogen fusion. Outer layers have to expand to let out the extra energy. It'll become a red giant, but core will get hot enough to ignite that helium. Yay, happy days. Triple alpha process will kick in, the helium flash. The sun will become a stable helium-burning star for roughly, 10% of its main sequence lifetime, so another billion-ish years or so. It'll run out of that helium, though, and the whole thing starts up again. The core shrinks, the outer layers expand, it gets unstable, it kind of starts to puff stuff off and ignite. And anyway, this is the stuff you're seeing that has been puffed off, has been blown off in that final stage as that core continues to shrink. It's hotter, denser, other layers on the outside fuse their elements and explosive bursts. If there's a companion star, which this one to me looks like there might be a companion down in there due to the cool symmetry on it, you can get these sort of symmetric things and make butterfly patterns as the star is blowing its outer layers completely apart, leaving behind the dead core, which is a white dwarf star. It'll actually form a carbon, maybe carbon and oxygen white dwarf, about the size of the Earth. It'll cool off. Starts out very, very hot and blue. Cool off, get colder, denser, and just fade into obscurity. But before that happens, they leave these beautiful nebulae, which are cool. So I'm going to go back one.
Can I show you my image that I did?
Yeah, Bill. So I'm going to stop sharing. So Bill is part of a class Bill is taking. I don't know where it's class. Now, which official nebula is that?
I just happened to pick that one. I found it in the data. I was looking for interesting nebulae and found that one and decided to
So is that actually NGC 6302?
That's it, exactly. That is it. In different wavelengths than they've got. But I love the detail. I had read that it's like it's one of the most interesting structural planetary nebulae in terms of what's going on in there. So
yeah, well, I have another one here for you since we're talking planetary nebulae.
I like how you said it was like butterfly shaped, but then like my brain was also like, oh yeah, Wu-Tang shaped as well. So it just
sure
works perfectly. So
Is this sharing? I have no idea what I'm doing.
Yes,
here.
it is, and that's very beautiful.
Yeah. So here's yet another planetary nebula. You can see this sort of hot, puffed up structure, but notice deep down inside where I'm moving the mouse in a circle, which I hope is working, you see almost a ring-like shape. And right in the very center is a little bright point. That's probably the white dwarf, or what will become the white dwarf. So this is just a gorgeous object. These planetary nebulae are really, really pretty things. And anyway, our sun is destined to do that. It'll wipe out the Earth when it does. Yay.
Cheers.
It'll wipe it clean, everybody. It'll scorch it.
The red giant phase engulf Earth, and some people even think maybe Mars. Yeah, let's drink to that.
Yeah, well, we're screwed either way. So,
well, I've been thinking about this. Maybe I'll bring up my half-eaten grapefruit. If I hold it this way, it's like a magic trick. It looks like it's not.
Wow.
That's right.
Ah! How'd you do that?
I know. Don't look. The magic things happen. Anyway, here's our planet, and I've been thinking about it. If we spin, say, this way, so we're looking, would that be North Pole down?
Mm-hmm. South Pole, actually.
South Pole. So this way is North Pole. Let's be South Polar centric. So staring at the South Pole, Earth is spinning like this. Now, which direction does our grapefruit Earth orbit if we're spinning this way? I think we go that way, right?
Yes, I think you're right. Yeah.
Yeah, to your right.
Yeah, my right's that way. So if that helps, I don't know. Anyway, what I've been thinking is if we fire...
No, the opposite way. Because if that's the South Pole going clockwise...
We have to put the sun off the direction.
I'm so confused.
I'm confused. No, I can only do it from the north up. How terrible is that?
All right.
We're gonna
having a drink.
Our juicy, juicy grapefruit Earth. Our sun is going to be up in the lamp, up in that corner. So there's our bright sun.
But then it won't rotate that way.
Up in there. Everybody see our sun? And here's our grapefruit. And we know we orbit this direction around the sun when viewed from the north. We lost Jared altogether. We scared him away. He'll be back. So there's our grapefruit going. Now, I have often thought, here we've entered daytime. Here's noon when we're facing the sun. And right over here, where my finger was holding it, is sunset. If we launch fireworks every sunset, and we're launching them up into the sky, shouldn't that be accelerating the Earth?
You know, a tiny little fraction. Yes, it has to, right?
I would think so. So we're accelerating the Earth a little bit, which means if we're accelerating the Earth a little bit, we're moving ourselves a little bit away from the sun because we're moving us a little faster than gravity wants to hold on to us. So we're slowly moving the Earth away from the sun. So in order to avoid being eaten by the red giant, we need more fireworks.
Oh, that's an excellent point. Yeah. That is an excellent point.
Yeah, I think this is entirely sound. Anybody on the YouTube stream on our chat want to contest that? Jared's gone. Let's say super nice things about him. And when he gets back, stop and act guilty. That is a really good plan. I like it.
You know what? Let's
Jared, I don't know how we're going to hold this thing together without Jared on the stream. Holy crud.
I'm back.
You missed it all, but I worked it all the details. So here it is in fast form. So here's our sun. Here's our grapefruit Earth. We go like this around the sun. So time passes. Sunrise is here. Noon is here. Sunset's over here as we spin around. If we fire fireworks every sunset, aren't we accelerating the Earth on our orbit? We're speeding us up and thereby slowly moving the Earth away from our sun.
Yes, technically.
Yeah. And all this means is to avoid being eaten by the red giant, we need more fireworks.
You're not wrong. You're not wrong.
Fire them at noon, though. We want to fire them off at noon. And who's going to do that?
No, noon pushes us the wrong way.
Yeah.
Oh, yes. Yeah. Well, then, but here's the thing. Oh, there's a compensatory thing here. Because you're saying at sunset, we tend to fire fireworks. But you go to Disneyland, it's like 9:30, 10 at night. So it's really...
That's on daylight savings time, so you move for it. So it's more like 8, and you're closer to sunset than you are to midnight.
So are you saying if we get rid of daylight savings time, we might save the Earth?
We
From
can
that.
so also okay,
Yes.
fine, right. You're right. So we can have fireworks, but we have to start the fireworks an hour before sunset, and we end them an hour after sunset.
Yeah,
So
they
a
can't-
2-hour period of fireworks. It'll all balance
Mm.
out. The Earth will accelerate. We'll be moved away from the hot red giant sun, and we'll save humanity.
We will.
I just, make sure that the fireworks are being shot off in the right vector so that the force is applied correctly, and it's gravy. Nothing could go wrong.
I still say if we just do enough fireworks, you'll have people airing a little bit this way, people airing a little bit that way, and it'll all balance out. And as long as we have enough of them.
Somebody could do the math to figure out exactly what effect that has, and it would be, of course, so infinitesimal. But
don't look at me. I'm an experimentalist. I'm an observer.
I know. I'm just saying.
I'm fireworks.
Somebody meant Jared here. So
I've done math for other things for figuring out like launch thrusts and things like that. Like with the space shuttle, I actually did the math to figure out how many farts it would take to get the shuttle on orbit. So,
how did you measure the force of an individual fart?
You really have to think about it, because in general, what we're looking at is basically mass, velocity of the mass, and how much energy is imparted from that.
Yeah.
So you have to think about like a really big fart, which is like a liter's worth of gas. So that's pretty big. And then you think about sort of in terms of like, what's its composition? Well, it's mostly going to be nitrogen and oxygen. So you can get those, and you can get the molar masses of those and figure it out. And you have to think about exit velocity as well, which will vary from person to person because of the nozzle. And the exit velocity is usually just about 8 to 9 meters per second, roughly, on average. So you actually end up making about 4 to 5 millionths of a Newton pound of force from that.
But we got to go back, because you think that a fart will travel like 25 feet in 1 second?
Per second. Oh, well, exiting, yes. Once it starts to mix into the air almost immediately after release, then it slows down significantly.
Well, as long as we're on this topic, did you see the news about the spread of the virus in toilets with the fountains that come up out of the toilet, and how that could spread? I forget how many million viral particles in these fountains of poop. I believe it.
Yeah, absolutely.
But what does this lead to? Are people on their travels just going to be by the side of the road? And that's a health hazard.
People leaving our stream is what I think it leads to.
This is not going to be good, but I don't know what the solution is.
Yeah.
I mean, it worked for humanity up until like 100 years ago when we started making that illegal. Nothing bad.
Nothing could be bad about that.
Right?
Nothing at all, of course.
Very good.
So I'm looking back at the space news here and seeing what there was. And of course, there hasn't been a whole lot. There's the story about why pulsars are so bright, but that looks like something I'll actually have to read.
Why are they?
I don't know. Well, I don't know why. I did notice. What do you think about them, SpaceX continuing to launch the Starlink satellites? Has anybody gone and looked for the ones that were supposedly darkened to make them harder to spot, give them less chance of interfering with astronomy?
So if I remember correctly, on the launch in January, there was one satellite where they had done a coating on it to change its albedo, or how much light it reflects. And then on, I want to say the Starlink launch after the last one, or the most recent one that they just did, they launched one that had a system that would allow it to cover the antennae so that it would be dark there as well. And I haven't seen anything yet from anybody. Usually a guy I look at is Jonathan McDowell, who's one of the astrophysicists at, oh my gosh, I'm going to completely forget it. I think it's the Smithsonian. He's sort of like the guy to go to if you're going to look at stuff that's happening in orbit around the Earth and things. And I haven't heard anything from him about that. So.
I'm really torn. I hate the messing with astronomy so much, but intention and the the reason for doing this is sort of noble at the same time, to spread internet all over the world to people who can't get access otherwise. But
well, but that's not their intention. Their intention is to profit.
Yeah, but you know what? I think if Elon Musk just wanted to make money, he would find, there's a way I
don't know. Like, you look at where these satellites are deployed, they are not to give internet to South America and Africa. The current batch the current batches he is launching crisscross Europe and North America.
Yeah,
all the time.
We're going to start beta using here in North America and Europe. They're not going to be deploying anything to South America or Africa or other orbital planes until probably after they get the initial batch up.
Yeah. So that is intentional, so that they could be tested with technologically.
I feel like too, there's also a intentional design in that as well, because there has not been anything said about how much Starlink is actually going to cost. And to have a satellite receiver in your house, it's pretty expensive. If you, but I mean, if you're mass manufacturing satellites like they're doing with Starlink, and which is bringing the cost of those down, yeah, you might be able to mass manufacture receivers as well. So you could bring those costs down. Nothing yet though about like how much access is. But if you're covering North America and Europe, it sounds like you're not going to be starting off with what I would call a entry-level cost of, say, internet in Africa or internet in South America or somewhere else.
I think it'll be competitively priced, is my guess. If anything, he's going to want to bring internet to all his Teslas. He's going to be like, I want my network. We're going to be able to do whatever we want. Hey, what number did we come up with, by the way, when we did the Drake equation last month? I don't remember. We could check our own stream, but I'm not going to go look at that, because there's a new estimate. June 16th, 2020. This was an article on Universe Today. They're claiming a number, and I'm wondering if they stole it from us.
What? Oh, wow. What is their number?
I think our number was much, much bigger. Their number was 36, plus or minus a few dozen, depending on the assumptions.
Just in the Milky Way?
Just in the Milky Way.
36?
36. It seems like there would be more.
Plus total? Or at any given time?
How many were there on Star Trek?
Well, that's right now. Right now. Like, if we were to go out there, hey, everybody, we'd get 36 replies, assuming we could talk instantly.
No, I'm not buying that.
I'm hoping it's way more. And like I say, Star Trek, I mean, look how many there were there.
Now,
so.
I can't see what emoji Sarah Vincent. Oh, no, that's at Sarah Vincent Pinsky's doing.
That's a face palm.
Good. I thought it was a face palm. I hope that she wasn't face palming at us, which she has every right to do.
Hey, Sarah Vincent, I have something for you. If you're there and you can take 5 minutes out, go through our stream from last show and see.
Wait, what was our prediction? Anybody remember what we predicted? I thought it was my.
Hey.
Anyway.
Hey, viewer, stop watching this and go look at our old show.
That's right. You can do both.
Oh, this is cool. All right. So I'm going to show some pictures of Phobos.
By the way, just want to say we still do have questions that we did not get to in our chat room. We've got like 4 or 5 questions.
Like what? You have to keep me on track here. I'm not responsible for any of
this. Oh my gosh.
Oh, my fault.
Yeah, thanks. Way to go, Doc. Where are some of the... So Space TV actually has a really good one that I quite like to ask all of us, which is, what do each of you personally think is the most interesting mystery in the universe?
I'll go last. Bill.
Well, it changes.
Where did the other half of the grapefruit go?
That's right. Where's the other half of that grapefruit? What happened?
Well, it's a mystery to me, at least.
The Onion did a thing where the oil companies figured out the fastest way to get all the oil is just cut the earth in half and just. So I want to say right now I'm really obsessed with FRBs, as you saw in our last time we talked about stuff, because they're just getting weirder and weirder.
Now let me jump in here, because a lot of people don't know what FRBs are. FRBs are fast radio bursts, and
Yes.
they are sudden bursts of, believe it or not, radio waves that our radio telescopes are picking up. Now, we just talked about this in a meeting the other day, and it was, there are how many total out there? that there are hundreds of them, and then a dozen or so. Yeah, I think around 100 of them we've seen, and something around a dozen of them or so repeat. Now,
yeah, they were surprised when they first saw a repeating one because they thought that this was just so much energy being released. It's radio waves are low energy, but the intensity was so high. There was so much coming out. That's so cute.
Yeah, I'm sorry, Bill.
I know we have to all stop talking.
Yeah, sorry. I couldn't help it. That's part of being cute. But anyway, we didn't know where they are. But it's true. We still don't know what's causing them, though. But a repeating one means that maybe they're not all cataclysmic. We used to think that these things are so powerful that it was a star blowing up and it's no longer there at all. Well, if they're repeating, that can't be happening.
Right. And now there's one that's actually periodic. It's actually doing it in a sort of rhythmic way. But let me just say that my ongoing biggest question in all of cosmology for me right now in astronomy is it possible to have an infinite universe that is expanding? And a flat infinite universe.
Well, but
because the universe is expanding.
You just said your biggest mystery was fast radio bursts. I'm not going to try and answer this other.
I said that's no, we can't answer. The other one is too. We just don't. That's like the topology of the universe.
No, I think it's answerable. I just am not to the end of the second or third time I'm taking a general relativity course.
Okay.
I've got hope, though. This time it's all making sense. Kind of.
I would love it later.
The mathematics is a little wonky still, but whatever. You try and do matrices.
Oh, I know.
Not easy. But anyway, so Jared, what's your biggest mystery in the universe that you want to see solved?
My biggest mystery in the universe that I want to see solved is the Fermi paradox, just because it genuinely doesn't make any sense. If life is so abundant, I mean, just here on Earth, look at all the different types of life that are here. Where is everybody? What the hell's going on out there? Is it really 36? It's being suggested in that? I mean, I feel like that's like a super low end estimate. That's like beyond pessimistic. That's like somebody who carries an umbrella with them.
Well, we're gonna lose Jared here again, so I'll step in. It is a little pessimistic in the 36. But at the same time, it does answer the Fermi paradox. Wait, here it comes. The Fermi paradox, by the way, is that question. Fermi posed it. If you have civilizations out there that are spacefaring or communicative, sending signals, and assume each one can go and expand to a new star within a reasonable number of time. Let's say it takes 100 years to build a spacecraft, once you're spacefaring, to put new people on it, to send them out to go colonize another star. And even if it takes them 1,000 years to get to that next star, so it's 100,000 years that it takes to move to another star, that's nothing compared to the billions of years in the universe. And at first you have one, and then you've gone to two. Well, then those two send out. It's exponential growth. So in 100,000 years, those two send out two. Then you have 4 civilizations sending out spacecraft in 100,000 years. Then you got 8, you got 16. So pretty soon you've got, terabytes of civilizations. Okay, not bytes, but tera civilizations. I did that on purpose. Terra, see what I did there? Earth, Terra. Anyway, I know.
I got it.
Okay, good. Nobody in the YouTube audience did anything, but they're a good 15, 18 seconds behind us on this. So
yeah, give them some time.
I just want to say it could be that there's our solar system, and then the center of the galaxy, and then the other 35 are all at the other end. And they're all talking.
Yeah, but again, Fermi paradox is that these civilizations keep spreading. Well, fairly rapidly, within billions-ish of years, you go to every single star. Mm-hmm. So even if it took them 5 billion years to kick this process off, 6, 7, we're 13.7 billion years in. Where are they? They should have come to Earth and been like, "Yo, how are ya?" Well, I have a thought on it. One, space travel is way harder than we think it is.
Yeah. Oh my gosh, are you kidding me?
Yeah, exactly. So,
God,
this notion of let's just go populate another star, super hard to do. So maybe instead of being every 100,000 years, maybe it's feasible every 50 million. And even then, when you get to the next one, maybe it's maybe you just give up and you're like, why should we put our time and energy into this? How about we just practice birth control? and we're pretty good on this planet. Everything's cool. And that, I don't know, as an intelligent individual, what incentive do I have to spread humanity throughout the galaxy? I mean, first of all, look what we've done here. So, Jared, we need to have a talk. I'm not sure about your goal of pushing rocketry into the future. It might be a bad thing for the rest of the world.
Well, so I think that.
But that could be the solution to the Fermi paradox, is that maybe it's just really, really hard to do it.
I kind of feel the same way, that there's a certain point where life just sort of goes, we're over it, kind of with it. But I also feel like it's not necessarily life saying we're over it. It's life saying, well, we personally don't really need to be doing this. So we're going to develop like a robotic system that can go out and handle this for us. So I would be very surprised if like your first life you find that's like out of solar system, if you will, extraterrestrial life, or actually let's say out of solar system, just in case.
Oh, he froze again.
He did.
He was right in the middle of a great sentence.
Because I shook my laptop, it might be. You weren't a great.
I can't. What is up with this internet? I swear to God, am I back? Do you have me back?
We're back.
Am I fully back.
Good. Yes.
What you're saying that what we're going to find is V'ger.
Yeah, actually, I just feel like I don't feel like we're actually going to end up finding like you or me or something that you could easily converse with right out of the gate. I feel like you'll find something that is basically like a robotic scout being sent out for it. I think that there's an actual technical term for it, and I think the technical term is called a Bracewell probe, if I remember correctly. But I also probably have been correct on that as well.
Yeah, I know what you mean though. Then probes make sense. One, I have to wonder if there's a way to communicate through the universe at speeds faster than light by not using the universe as your medium of communication. If you can do that, then you could send probes places, use that subspace to send the message. And all of a sudden, it makes way more sense to send probes to go look at things. Maybe the answer of why nobody has been to Earth, or why we don't think they've been here, is that they came a long time ago. If you're out, and instead of colonizing, let's say they have an interest in just cataloging. Back to that question of how could we catalog every star in the entire universe. What if they are just cataloging, going from place to place and looking and saying what's there? You came across Earth maybe shortly after the event that took out the dinosaurs. You might be like, interesting place, but not much going on here. We'll come back later. Well, not that much time has passed. It's only been, millions of years. They might just have not gotten around to coming back to see what's happened yet. And when they come back, they'll be like, whoa, these are those shrew-like things? These are, what?
Yeah,
what happened here? So I don't know. I kind of wonder. I mean, it's really arrogant of us to assume as humans who have been here as a, record-keeping civilization for really thousands of years. We've been keeping
10,000 years.
To then, because in the several thousand years, the aliens didn't drop by and be like, yo, how's it going? That they weren't here earlier. They might have been. Now, this is not going along with all that ancient aliens nonsense. My cat is biting me to remind me to say the show Ancient Aliens is nonsense. Right, Horton? Yeah, bite me for bringing up Ancient Aliens. Nonsense. Good fun to watch, but complete nonsense. They will do things like, and nobody knows where these people went. Could it have been aliens that abducted them? Well, nobody knows means they didn't bother to go find the expert that studies these people and knows where they went and why. That they went and called up a couple of people on, I don't know, a helpline at an 800 number or something. And we don't know. Like, good enough. Nobody knows where they went. But if you take the time to actually research it, most of the things they pose as nobody knows are not real arguments. The show doesn't know and they're pretending. And then, could it be aliens?
We're skipping just humanity and its self-destructive tendencies. I mean, the reason we don't maybe leave the planet and go find other life is because of, our wars, our stupidity, we don't listen to our intelligent people sometimes as we, I don't want to get into that.
Well, that's the built-in saving the universe. If our own problems prevent us from going out there and spreading those problems in the universe, well, yay. Anyway, I want to get to what my biggest unsolved mystery in the universe
Yeah, please.
well, one is there life outside of Earth? We don't know. And I think that's a big mystery. And I'll just keep it open to just life in general. Oftentimes people want intelligent life. In our last show, we actually talked Drake equation where we're looking for intelligence. I just want to know life. And part of that reason is my money is on yes. My money is firmly on yes, and that it's even elsewhere in our solar system. And I think it may even be proved that, well, I don't know. I can't decide which is more exciting. Independently, evolved life would be incredibly exciting because it would say that if you give life the chance to evolve, it does. So if we go to Mars or Europa or one of these places, we think there might be an ocean and a thermal source and life could evolve, and we look at it and it has maybe a DNA helix that goes the other direction. Or it's built on, some other form of it, a hoop-shaped DNA that we've seen weird things here on Earth, but you go there, maybe it's characteristically different. We can prove it has nothing to do with the life here on Earth. Well, that would say that life evolves readily and easily, and wherever you give it a chance, it's going to do it. However, it's also super cool, the notion of panspermia. How do you say it?
Panspermia.
Panspermia. I've lost the ability to talk. Thank you, Bourbon. That notion of if life formed on Mars first, because Mars was wet, it was warm long before Earth was, long before meaning millions of years. Maybe life got started there. Along comes giant asteroid, smashes into Mars, blows material off out of the frozen North Pole. Little bacteria float here. Little tardigrades come down to Earth and say, hey, let's colonize this place. It's pretty good now, and maybe we're all Martians. That's a super fun idea, but it also doesn't tell us. It tells us that life is hardy because it can move from planet to planet, but it doesn't tell us that it can evolve readily all over the place. So
Except
learn a lot.
It still begs the question, how did it start initially, wherever it initially came from, Mars or elsewhere?
Right.
Dice.
Well, there are actually some folks that believe you could start life within, believe it or not, a big comet. You do the calculations, and if you have the amino acids and some of the stuff that we think is cooked up in nebulae, the sugars and things that we're seeing, you take these, you start to make this snowball. Well, you pile on enough material, the center of it melts, we think. And you got this melty center. If you've got the basic building blocks of life, and if it can stay melty for a few million years, they were predicting, maybe that's long enough that you get some really basic biology going. Then you freeze it in place, and then you smash these things into the planets once they're done with being the hellish lava worlds that doesn't let anything happen. And then life is everywhere. So who knows? These are the questions that I think are super exciting. We're on the verge of learning about. But instead of, I hate to say it, but instead of funding missions and studies to go learn all these amazing things, in some ways, I honestly think we need to take a good long look at what we're doing as a species and the direction we're heading, and think about how it's going. I mean, I realize the science budget is very small, and I don't want to call it spin-offs, but the things that come from the basic research benefit humanity greatly, especially the space program and others. But at the moment, I wish that all the super smart people in the world out there doing science that is part of the great spectator science, at least, which is kind of astronomy. We're not making tires safer to drive on the road. We're not making better ventilators to save people's lives. We're doing cool stuff that blow people's minds. It's valuable. But maybe everybody needs to take 10 hours less a week and devote it to, fixing our problems here on Earth. I really want to say that in our last minute here. The issues we're facing, and I don't want to say I have the solutions. I said I wouldn't pose that. But one of my solutions is if everybody just stopped thinking their little bit of whatever they're trying to do was so super important and put 10 hours into asking how can they be part of the solution? Because I don't have all the answers. I don't know. But how can we contribute to solving some of these problems we face, whether it's climate change or whether it's what those wonderful bells are I'm hearing in the background, reminding me it must be 9 p.m.
My grandfather clock.
Yeah, it's reminding
which my father purchased. So
Oh, I don't know, that's blowing my mind, Jared. But anyway, I just think if we all take a little time and we dedicate ourselves to trying to solve the world's issues, the world's problems, and do it through listening rather than proclaiming we all have the answer, maybe we'll find the actual answers, because shouting at each other doesn't seem to be solving it. So
You should set up a forum for that. You should do that.
where I just shout at people. I do that too often.
No, not shout at people. Find reasonable people and pose the questions and say, how do we do this? Because I think it's basically you have to fix human nature, which is very difficult.
I think it's very difficult, but I'm no good at that. I have all sorts of failings about how the way I handle things. But I can say I hope people take some time and they devote themselves to just trying to solve some issues. And climate change is a huge one. Of course, the social unrest we're seeing now and the uprising, the revolution, whatever you want to call it. In my opinion, we're seeing it has a kernel of a revolutionary feel in my mind. And honestly, until our freedoms and until justice is applied equally, it's a privilege. It just is. And I don't know the right solution, and I can't say I've experienced it, but I've experienced the privilege. So I can say that much. And until we make everybody have those privileges, that's what they are. They're not rights. They're not freedoms. They're privileges. So I'll leave it at that. But anyway, I'll let you say a final word. I'm happy to be here tonight. So thank you, Bill, and thank you, Jared, for joining us. And any final words from you guys?
Just get out there, take a look. Moon's going to be coming up in the next week. So take your time, go out, look at it, enjoy it.
Yeah. And now that I have my new streaming computer going, I'm going to dedicate myself to I'm hoping to put my other computer, my old PC and everything into another smaller box and turn it into one that we can use to bring you live images through some of these telescopes that have been dedicated and donated to Black Rock Observatory. So we'll do that in the future. Bill, what do you think? What do you think folks should do in the next month before we come back with another show?
Oh boy, what to do in the next month? I don't even know what to do in the next day, but I don't know. I have to say that I really like your idea in terms of actually creating a structure to have a forum of people very, very multidisciplinary and say these are some major issues and problems that are keeping us from being what we really could be, and what do we do? Yeah,
and I think if we're going to solve the problems, we need to go to the folks that are experiencing the problems.
That's true.
Climate change, I'm perfectly happy to talk about, but in terms of Black Lives Matter and some of the other social changes that need to happen, I think we need to listen to those leaders and find out what we should do. But yeah, you're right. We should listen to people. I think it goes a long way. So Bill, you take my idea and run with it.
What I just suggested to you, but okay.
I know, but I don't have time for that. I got regular work, and we do hope to take the show on the road at some point. Like I keep saying every episode, we're making connections. It's great to be doing. We're reaching out to folks, laying the groundwork that eventually maybe we can travel. I don't know whether it's going to be 4 times a year. We're able to do it 2 times a year. We only have so much vacation time, but eventually we're going to start doing some stuff from the road, and we want to go worldwide. So if you're out there watching this and you know something cool that is out there that we should come see in the future, hit us up. Or if you just want to be on this show, if you made it this far, give us a like, ring the bell, and give us a follow. And with that, I think I'm going to shut down the stream if I can figure out how to do it here and say goodbye.
Thank you very much.
All right.
Thank you, everybody. Join us next month. It'll be about a month from now. We'll have our next episode. And thanks for hanging in there. Good night.
Good night.